Hello, we're going to continue our discussion on wave energy, and today we're going to discuss the Doppler effect. And the Doppler effect is an important characteristics of wave we would like to review or understand because it manifests itself in a lot of applications. The Doppler effect is used quite extensively in astronomy, and probably the most famous example is the redshift that Hubble, the astronomer who identified the redshift, and he was able to prove that the universe was expanding and not static or contracting. Because up until Hubble, the main theory on the universe was that the universe was static or would contract, and he proved that the opposite is true using the Doppler effect measurements, that the universe is actually continuing to expand. And this brought up a whole new theories in physics or astronomy or astrophysics in terms of dark matter and dark energy. Radar, it's used quite extensively in radar and weather radar, and versus traditional radar, the original traditional radar just used sound pulses and the reflected beam. They could determine an object's distance, altitude, and things like that, like an airplane. But Doppler radar enables you're not really relying on the amplitude of the sine wave. You're looking at the frequency shift. And when you look at the frequency shift, you can detect the movement of an object. And where in weather radar, where this is very valuable and used quite extensively, is in storms. It can detect the movement of rain and wind shear and things like that, which could be a danger to aviation. And so Doppler effect is used quite extensively in aviation and in radar in general. And then ultrasound uses the Doppler effect, for example, to determine the velocity of blood in a blood vessel. So what is Doppler effect? So if we go back to our sine wave, and again, wave energy we represent by a sine wave, we see that the period, or when the wave repeats, is from, in this case, from the crest to crest, or when it's at max amplitude. That's what we define as the wavelength, and it's also the period. The period is the time in seconds for the wavelength to repeat. And then if you recall that the frequency is 1 over the period, and that's in hertz. So, and that normalizes it to 1 second. So it's how many times this wave will repeat per second is what frequency is. And period is just the inverse of frequency, which is how long it takes to repeat one cycle. And then the wavelength is actually in units of meters, and that's the physical length of the wave as it propagates through space. Now again, as I said, this Doppler effect applies to electromagnetic radiation or waves, and also to sound waves. So before I begin the discussion on the Doppler, or explain the Doppler effect, there's also some pretty good videos out there. I posted a couple of them on Canvas as well, and I would encourage you to take a look at them. But before I do that, one thing I'd like to explain is how we graphically look at waves, whether it's electromagnetic waves or sound waves. So if you look at this wave on a side view, you see that it looks like a roller coaster. And again, the crest to crest would be the wavelength or the period. So just keep in mind the crest, these 2 points here. Now if we were to look, let's say, down on this wave, this is how we describe a wave propagation graphically. So what does that mean? Let's say we have a source here that's emitting electromagnetic energy, or sound wave. So this is a point source, and it could be, as I said, electromagnetic wave or a sound wave. And if we were to draw the waves that are, the energy waves that are emitted out of this point source, this is an omnidirectional in all directions, you could see, we could kind of sketch the wave as it propagates out. Something like that. And something like this on the horizontal, and it's propagating out. Where this is the amplitude, minus amplitude, and then the peak to peak here would be the wavelength and the period. So that's from this diagram here. But however, that gets kind of busy, and it's kind of hard to draw that out. Instead, what we do is we draw just the points of interest, and that, for example, would be the amplitude. So what we want to do is capture these points here where the wave is at its max amplitude, and then the time or the length between these 2 points is the wavelength and the period if we were in time, or the wavelength in meters. So here's our wave propagating out, and what we would do to represent this is we're really not interested in every little detail position along this wavelength, because we know it's periodic. In other words, we know it repeats, it's consistent. So we don't have to physically, or at least conceptually, know every point every point of where the particle, the wave energy, is traveling on the sine wave. So what we do is we just capture the peaks. So we draw the dot here, are the peaks, and that would represent these dots here from peak to peak. So now again, the wave is traveling in all directions. It's omni-wave, and so what we do is we just draw a circle, concentric circle around our source. That's supposed to be a circle, and then from peak to peak we draw another circle. And forgive my drawing here because it's not very accurate. But essentially what I'm trying to do, and I hope you get the gist here, is that these distances here represent the wavelength of the particular wave, and they should all be the same. They should all be equal distance, which are not, because that's my drawing's not to scale. So instead of drawing this sine wave, we just draw the peaks. So the distance between these 2 peaks here, if we were looking down on the sine wave, if we were looking down, what we would see, and if we could just see the peaks, this is what we would see. So it's propagating out. And that's how we represent the pictorially or graphically this energy wave traveling out. And a good example would be dropping a stone in water. If you ever drop a stone in water, you kind of see the ripple. We call it the ripple effect. And you kind of notice the ripple effect due to the reflection of the light. It's consistently, we can kind of see the peaks and the troughs of the wave as it propagates outwards. So here's a better representation. So you can see these concentric circles, and these represent the wave energy propagating out from the point source. And the equal distance spaced apart, it should be the distance between them is the wavelength in meters, or it's the period in time of one complete cycle. And so that's another way we can represent a sine wave moving out. And then here's an example of water, which water can, can have waves, properties of wave energy traveling through a liquid. And you can see, a similar type of concentric circle, and these represent the ripples, but it's really a wave propagating outwards. So now what happens if the source here emits a sound wave? Let's just use a sound wave, for example, at a specific frequency. We can call that F1. And let's say F1 is 200 hertz. And if you're an observer over here, eventually that wave front, or the compression wave, is going to hit you, and you're going to pick up that sound. And the frequency you're going to hear it, if you're not moving, if you're stationary, that means your velocity of the observer is 0, and then the velocity of the source is 0 meters per second. So both the source of the wave, the sound energy, and the observer, they're both not moving, then you would hear the sound at the same frequency as the source emitted, and that would be, at the observer, you would also hear 200 hertz. And that kind of makes sense. Now what becomes interesting is, what if the source is moving while it's emitting this sound wave, or what if the observer is moving, or both? Then what happens? And that's where the Doppler effect comes into play. So let's take one example, and this example is one of the typical ones, is let's say an ambulance has a speaker and it has its siren on, and it's moving at some velocity now of the source. And you're an observer, and your velocity is 0, so you're stationary. However, the ambulance is moving. If we were to look at the first case 1, let's look at case 1 where, again, the ambulance is not moving, it's stationary, and the source velocity is 0. And again, the observer is not moving. Then the wave energy would propagate out at equal spaces towards you. until it reaches you, and then you would hear it at the same frequency it's being emitted. However, if the ambulance is moving, what happens is, if you conceptually, if you think about it, when it's emitting these peaks, right? This peak, this is again the peak of the sine waves. If he's moving, he moves a distance, whatever distance is speed d, before he emits the next wave, and his next sound wave comes out. Well, if he's moving, the distance now starts to shorten of the wavelength. So what happens is the wave starts to compress. In other words, the spacing gets closer and closer as he's moving towards you. So the wave now that reaches you, the wavelength is shorter. So if this is the wavelength of the stationary, this spacing here of the stationary ambulance, this is the new wavelength of the ambulance now that's moving. So the wavelength of the ambulance moving is going to be less than the wavelength of the stationary ambulance, which implies that the frequency that you hear of the moving ambulance is going to be higher. So you're going to hear a higher pitch sound. And electromagnetic energy, if this is a star and if it's moving towards you, what you would see is what's called the blue shift, because the wavelength of the light, or the electromagnetic energy in the blue that's moving toward you, would compress, and the frequency would shift to the blue region. Similarly, if the ambulance was moving away from you in this direction, the velocity of the ambulance, the source, the wavelengths would spread out. They would get further apart. And the frequency of the observer that you would hear, if this is the frequency of the source, the frequency of the observer, you would hear a slower frequency than with the observer. So the frequency of the observer would be less than the frequency of the source if the ambulance is moving away from you. And if this was a star, what would happen is what is called the redshift. And the observer here, the person on Earth, the astronomer, would see the change towards the red end of the spectrum of the light. And remember, red in electromagnetic energy, the blue and red is how we perceive kind of the frequency or the energy in the wave. So just to throw some relative numbers out there, again, if the source, in this case a star, is moving towards the observer on Earth, the waves compress. They get closer, the spacing gets closer together. That means the wavelengths get shorter, and you shift to the blue spectrum. And blue light wavelength is around 460 nanometers, which is 460 times 10 to the minus 9 meters. And the frequency of around blue light is around 620 terahertz, or 620 times 10 to the 12 hertz. So it's moving. It's a pretty fast wave, even in the blue spectrum. However, if the star is moving away from the observer, then the waves uncompress or decompress. The spacing of the wavelengths gets further apart. The wave kind of stretches, and the frequency gets slower. And the frequency in the red spectrum is around 430 terahertz versus 620 hertz of blue spectrum. So the wavelengths, the frequency gets lower, but the wavelength gets longer. So the wavelength of a red spectrum approaches 700 nanometers, whereas the wavelength of a blue light is around 460 nanometers. And that's the Doppler effect. So if you look at, let's say, traditional radar, that a traditional radar would have sent a signal or an energy pulse out, electromagnetic energy pulse, let's say, to detect an airplane or something aluminum. And what it's looking for is the energy to bounce off or reflect back from the airplane back to the source, which has an antenna to pick that up. And what you're looking for in traditional radar is you're looking for a change in the amplitude. So this is the signal you send. And some of that energy, remember when the wave hits something of a different density, so this is the density of air, and obviously this is the density of aluminum if it's an airplane, there's going to be a density boundary. some of that energy is going to be reflected back towards the source. And so what you're trying to detect is that little amplitude of energy that's reflected back. And that's what you receive at the radar station, and then you can determine the time of the wave, how long it took to propagate, how long it took to come back, and so you can estimate the distance the object is from the radar source. What's nice about Doppler radar is it doesn't really rely on the amplitude. What it relies on is a frequency shift. So what happens is if you're the source and you send out a wave energy at a certain frequency, let's say this frequency of the source here, and then again it strikes an object, which is an airplane out here, some of that energy gets reflected back. But what you're looking for is you're not looking for an amplitude change. What you're looking for is if this is your source signal that you sent out at a certain frequency, let's say F source, and you get a return signal, what you're really trying to look for is just a shift in the frequency. So what you're looking for is a change in the frequency of the return signal, and it could just slightly be moving just slightly faster than what you sent out. So what you're looking for really is a change between the return signal comes back at a different frequency, the return signal, than what you sent out. Then you know that you've detected an object that's moving. And then also it's independent of amplitude of the signals, and you're just looking for a frequency shift. And what's good about Doppler radar, what advantage it has over the traditional radar that just looks at amplitude, is these, as you can see, these electromagnetic waves these wavelengths are very short. They're in the nanometer range. So the energy that comes back in the slight phase shift, you can detect very small objects that are moving. So for example, raindrops in a storm could be moving because of wind shear, could be moving down, for example, in wind shear. Traditional radar would be able to pick that up because it's just looking at the amplitude and the reflected energy off all these raindrops, but you're just going to get some reflected energy back, but it's not going to give you any information on the water drops or the raindrops moving in the storm. Whereas a Doppler radar, because it's looking at the phase shift, and because the wavelength is so small that what comes back, you get a slight shift in the frequency, you can detect the motion of a raindrop in a storm. And where this became valuable in avionics was when they had some accidents a while ago when a plane crashed because of the wind shear. Well, wind shear is when an airplane came in to land at, let's say, a runway, and it gets low in altitude, and you get a tornado or a storm. Let's say it's really typical in the South or in the Midwest. You get these microbursts where you get a thundercloud, and all of a sudden you get a burst of downward wind, and it's very strong and just vertically down. If a plane's landing and flies into this, it could lose lift, and there's not enough altitude to recover, and the plane could crash. And that actually happened. And a traditional radar wouldn't pick this up, but a Doppler radar, because of the way it operates in these wavelengths are so short, can pick up this microburst. So it can warn the pilot when he's coming in to land that there's a microburst, and for him to climb and get out of the microburst. So that's an example of where Doppler radar is used quite effectively in weather as a weather radar. And they also use it, if you ever see the movies about the storm chasers that are chasing tornadoes, they use Doppler radar because they can actually determine the wind speeds that's going on in the tornado itself using Doppler radar, because it's that fine of detailed measurements, just because you're looking for the phase shift or the change in the frequency. So here's the general equation for the Doppler effect to calculate the different change in frequency, or more importantly, maybe you'd want to determine the velocity of, let's say, the source or the observer. And just so we get the variables straight here, this is the frequency of the observer, and would equal the frequency of the source that emits the sound energy. In this case, it's sound energy, so this would be the frequency of the source here. This is what the frequency of the observer, what the observer would hear. This is the velocity of the observer. this is the velocity of the source. In this case, it's 0. And v, this term here, is the speed of the wave energy in the medium it's traveling. So that would be the speed of the wave in the medium. And for air, this is usually given in the problem. This would be, if it's sound wave, this would be the velocity of the wave traveling in air. And again, this value varies with density, temperature, and things like that on the air. So it's not a fixed number. And typically in problems, they'll give you this number, or you'd have to look it up and make an assumption. So again, this is the v here is the speed of the sound wave in the medium. This is the velocity of the observer. This is the velocity of the source. And then this is the frequency that the source emits. And then this is what the observer would hear in this case. And then if it's if the motion is towards the source, or if they're moving towards each other, then you want to make the values of the observer and the source positive. And if the cyclist, in this case, is moving away from the observer, then the value of v naught would be negative. And vs would be negative, but in this case, vs is 0. So that's how you interpret the equation and use it for determining the change in frequency. And that concludes this discussion on the Doppler effect. Thank you, and see you next time.